Right folks, today we're going to be looking at centripetal acceleration and centripetal force. Now to help us understand that, we're going to take a situation of just a little ball which we're going to spin round in a circle. Imagine you're standing holding a ball with a string in it. You spin it round and it goes in a circle, and it's got a radius r to the centre of the circle, and it's got a mass m, and it's got an angular velocity of omega, and it's got a linear velocity of v, and we draw that there. And it's not drawn brilliantly, it should be a tangent to the circle, but you get the idea. So if I draw the wee circle further round, then so that's what it should have been. Externally, if I put the wee ball gets to there, it's tangential linear velocities that way, or around here it's tangential velocities here. So you get the idea that wherever the ball is, it's got a linear velocity that's at a tangent to the circle. If I cut the string, it would shoot off in a straight line. It wouldn't go out the way, it would just go straight off at a tangent like that. Okay? So the ball's going in a circle like this, and there's a force acting towards it. To make it go in a circle, there has to be a force acting towards the centre of the circle, and that force is called the centripetal force, and that's applied by you in this case as you spin the ball around your head. And this is sometimes called centripetal, sometimes it's called central force or radial force, but that's the force towards the centre. For anything to go in a circle, then there has to be a force towards the centre of that circle, or it just won't go in a circle. There's no force acting out the way, that's what that arrow there means. There's only a force towards the centre. Okay? Okay, so let's take the situation of an object spinning. Let's look at in more detail. So there's an object that's spun in a circle, a ball on a string, right? And it starts off in this position here, call that A. And we're not going to take it the whole way around just to get some A, and it goes to B. Alright? It's just part of its journey. So it moves from A to B, and the angle in there between the points A and B, we're going to call that 2 theta. Now there's a good reason for that. And that's the linear velocity at A, call that U, initial velocity, and that's the final velocity at B. They're both linear velocities, and notice they're at tangents to the circle. So U is the initial at A, and V is the final at B. R is just the radius of the circle. So let's just define when a centripetal acceleration actually occurs. So centripetal acceleration occurs when an object moves in a circle, because the direction of the velocity of the object is constantly changing. This change in direction of velocity constitutes a change in velocity, and A acceleration is change in velocity over change in time, and so delta V is the change in velocity. Now it's not a size of the change, delta T is the change in time, it's a directional change, but that's a vectorial change. Because velocity is a vector, a change in direction is a different velocity. Okay, and that A there, if I can spell it right, is centripetal acceleration, sometimes called central acceleration, sometimes called radial acceleration, just to confuse you. I like centripetal because centripetal is just fun to say, and I think it's a more common use of word. But you need to know that there's a centripetal acceleration because the direction of the velocity, not just direction, the direction is changing. So let's take the final velocity and add it to the initial velocity vectorially. Now if we do that, what we get is this diagram here. We have, there's the final velocity v, there's the initial velocity u, but notice they're connected. So there's v, there's u, but they're connected tail to tail. So we don't really want that, you wouldn't draw it that way. We don't really want velocity, final velocity plus initial velocity. What we want is v minus u, because we know that a equals v minus u over t, So all we do is we turn the u vector upside down, that makes it minus u, and then we can draw this. There's our original v, it's a bit short, right? There's v, but this time u is pointing the other way. So now it's either connected correctly, so there's v and there's u, minus u I should say, and then you can draw, with a bit of help, you can draw the resultant vector from there to there. Now that resultant vector is the change in velocity. That's my delta v. Just give me a second here, I'm messing around with the... So that there is the resultant vector, and that is delta v, or change in. That's still 2 theta in there, and that's delta v. Now if I draw a line down the middle there to create a right angle, that becomes delta v over 2, and the other side is obviously delta v over 2. Now because I've got a right angle triangle, I can bring SOHCAHTOA into my calculations. So there's a right angle, and so what I can write is, okay, that sine theta, or 2 pi in this case, is going to be delta v over 2 times v. That should be delta v equals 2v sine theta. Now I forgot to be a 2, it should be sine 2 theta in there, but you get the idea. Okay, now delta t, the time it takes to get from A to B, call that delta t. And delta t is just going to be distance over speed. We're going to call that distance arc AB over the speed. So arc AB is from A to B. It's not that difficult. There's A, there's B. So the arc AB is from there to there. Okay, and that's our distance. So it's just this speed equals this over time because it's constant speed. It's really important to get that. We're really looking at constant speed just now, constant velocity, constant angular velocity, so it's not too challenging. Remember from the last video we did that in radian mode we can write, that's S, we can write theta equals S over R. In other words, S equals, in this case it's 2 theta equals S over R. So S equals 2 theta R, or R equals R, S equals R2 theta. So that's what we write for arc AB. That's S, and then that's what I've said, R, okay, and divided by V. That gives us a nice expression for delta t, and we have average acceleration is change in velocity over change in time. Okay, but we don't really want, we've already got an expression for change in velocity, and that change in velocity is 2v sine theta over r 2 theta over v. We can cancel some things here, the 2's can be cancelled out, which is good. So again, A average equals v sine theta, but we're going to change it a little bit, bring the v up. So that gives us v squared over r times sine theta over theta. Now, you'll see why we're doing this. Okay, and obviously to get A average to become an instantaneous acceleration, or just A, we have to make delta t as small as possible, which means if we make the time that we're measuring over really tiny, then the angle between A and B becomes tiny, so theta becomes really, really small. And if you take theta to be virtually, as well, really, really small, as theta tends to 0, then sine theta over theta becomes closer and closer to 1. You can try this yourself. It only works in radian mode. But if you take the sine of a really small number in radians, so 0.000001 over 0.00001, you get 1. And you can do that for yourselves. That'd be fun for you. So now, if you take the sine theta over theta to be 1, then you get v, you're left with A equals v squared over r, where A is the centripetal acceleration. Okay, but we've got a bonus equation here, so it's meters per second, that's really important. It's a centripetal acceleration is in the same units as acceleration, linear acceleration, so it's meters per second. But remember, v equals r omega, so I can substitute v equals r omega in for v, so I get v squared r squared over r, and it leaves me A equals r omega squared. So I've got two equations. A equals v squared over r equals r omega squared. And those are equations that you really have to know inside and out. Okay, so just take a note of that somewhere, find a bit of paper, write those down. For centripetal acceleration, v squared over r equals r omega squared. But we know that F equals ma. And all you do is you stick in, well, v squared over r for a in this one, and you get m times v squared over r, and that's the centripetal force, and mr omega squared. So F cent equals mv squared over r equals mr omega squared. And those are really, really important. So that basically means that to get something around a certain centripetal force to make something go at a certain velocity at a radius r, if it's got a mass m. Okay, so to make something go at a mass m at a velocity v at a radius r, you have to provide a centripetal force. That has to come from, it can come from friction if it's a car going around a roundabout, it can come from gravity if it's the moon going around the earth. But it's really important that's the force has to come from somewhere. Okay. Now, let's go back to this question. It's a simple wee question in many ways, but okay, so it's got a radius. The radius of the car going around this little track is 4 meters. The velocity of the car is 6 meters per second, and the mass of the car is 2.5. The first question says, calculate the radial or centripetal acceleration. Okay, don't need to mass for that just now. So just sticking numbers into the equation. A equals v squared over r. Plug in the numbers. So that's going to equal 36, well 6 squared is 36 over 4, which is going to give you 9 meters per second, and that's the centripetal acceleration or radial acceleration. Okay. And the next part of the question asks you calculate the radial force of friction is between the tires and the track is 23 newtons to show that the car can go round at 9 meters per second centripetal acceleration without coming off the track, or in other words, you can have a velocity of 6 meters per second without any problems. So you calculate, okay, what's the required centripetal force to make a car of mass 2.5 kilos go round a 4 meter radius track at 6 meters per second. So the centripetal force required for that to happen is 22.5 newtons. So the friction is 23, you're home and dry. There's no way that that car can come off because the centripetal force has been provided by friction, and it's sufficient to get you around, so it's greater than it. However, so it says force of friction is greater than the required F cent, therefore the car. But let's say that the velocity of the car is actually not 6 meters per second, but in fact is 7 meters per second. Can that wee car go around that track at 7 meters per second? Remember, the friction between the wheels and the track is still only 23 newtons available. So let's work out what centripetal force do you need to go around that track at 7 meters per second. So we're going to use F cent equals mv squared over r again, and we're going to work out what centripetal force is required to go around that track at 7 meters per second. So we calculate it out, stick it into mv squared over r, and we get 2.5 times 7 squared over r, which is 4. It gives you, let's work it through, and that gives you a total of 30.6 newtons. So you can see the required centripetal force is 30.6 newtons. You only have 23 newtons, so that car would come off at 7 meters per second. So it couldn't stand. So the required centripetal force is greater than the available centripetal force, which is 23 newtons from friction, and so it will come off. And anything, the centripetal force has to come from somewhere. So if a car is going around a corner and the force of friction is less than the required centripetal force to go around that corner, then the car will come off the corner. It's really important to get hold of that. That centripetal force has to come from somewhere, whether it be gravity, friction, tension in a string. It's not a separate force itself. It's a result of other forces. And if you get hold of that, you can really get a long way in centripetal acceleration. Okay, centripetal forces.